Okay, so questions about any of these? We can just talk through them all. The speed of the ball increases as it rolls down the incline, decreases as it rolls up an incline. What happens to the speed of the ball on the smooth horizontal surface? As it rolls, what's going to happen to its speed? Its motion is likely going to remain. If it slows down, it's going to slow down very, very slowly. What's going to cause it to slow down? Air resistance. And on slow-moving small objects, there's not a lot of air resistance. Number 2, the law of inertia states that no force is required to maintain motion. Why then do you have to keep pedaling your bike to maintain motion? Luis and Khalil and I went down and found a bike. We did. Why do you have to keep pedaling, gentlemen?
Friction.
Friction where?
In the bearings.
In the bearings of the wheel. So that's one place. So assuming the bike's just going, I just lifted the bike off the ground, we spun the wheel stopped by itself. Because there's friction in the bearings of the wheel. If you're riding the bike quickly, now all of a sudden you have to acknowledge air resistance as well. So there's a whole bunch, the bike is not a perfect system, it's not entirely frictionless. So there is friction specific places. This is why you must keep pedaling, because there are forces that are actually trying to stop you. Yes, Niraj. It is. It looks like this on the front. Unit 4, Newton's laws. Number 3, if you were in a spaceship and fired a cannonball into frictionless space, how much force would you have to exert on the ball to keep it going? Nothing, because it's frictionless. Nothing. It would go forever until it hit something. Number 4, an elephant and a mouse have the same weight, which is 0, in gravitational free space. If they were moving toward you with the same speed and they bump into you, would they bump into you with the same effect?
No, because the elephant has more mass.
The elephant has more mass, which means it has more inertia. So no, the elephant would definitely have a larger impact. What is the weight of a 2-kilogram container of yogurt? 19.62 newtons or 19.6 newtons, depending on which value you use for gravity. Yes. Number 6, a massive ball is suspended by a string from above, slowly pulled by a string from below, as seen in this figure down here. Is the string tension greater in the upper or lower spring? The upper one. Why? Why? Hands up. Luis was talking first.
The tension is greater in the upper string because there is more weight applied on it, because the gravity is being applied on the ball.
Yep.
And you are putting pressure in the one below, and the string is trying to handle these two forces by itself.
Right. So you're pulling down and gravity's pulling down. The string up top has to deal with both. Love it. So then, which of those two strings in that situation is more likely to break? The upper. Which property, mass or weight, is the thing that's important? Luis answered that one already. Weight. Gravity acting on that large ball. Now, 6b, if the string is like the bottom string, instead of like slowly being pulled, you yank it downwards. Which string is more likely to break? It is the bottom one. Why? No, actually that's not the reason why. Connor.
The mass of the string.
Nope.
No.
I know you know the answer, Luis and Khalil, because we talked about it yesterday. So I want to give some of your classmates a chance first. Tristan.
Because the ball's not moving, so it wants to stay not moving.
There it is. The inertia of the ball. Ball does not want to start moving, so the ball is going to resist the yank you just gave it, which is what's going to cause that smaller string to snap first. Love it. Which Khalil and Luis, that's what we were talking about yesterday, yeah? Number 7, if the head of a hammer is loose and you want to tighten it by banging it on the top of a workbench, why is it best to hold it with the handle down and smack the handle onto the workbench than to flip it upside down and to smack the hammer head onto the workbench? Khalil.
Because when you hit the handle stops, but the hammer head keeps going since they're not one thing.
Yeah, they're not like bolted together. The hammerhead is going to want to keep going. Why? And which has more inertia? Typically the head. The wood making the handle is going to be a lot lighter. The head of the hammer is going to have a lot more inertia. And so it's going to drive the head down further onto the handle. Cool. Love it. Questions about any of these 7? Relatively straightforward with inertia? Okay. Then I wanted you guys to go back and I wanted you to take a look through this. This was just kind of a lead up into the lesson that we were going to do today. Are there any questions about any of this? I think it was all fairly straightforward, except for the one typo that Tanjot found. In part 2, where I wanted you to work on friction, I wanted you to click on the friction tab, not the motion tab, which didn't seem to be an issue for anybody, because lots of people were there already when that mistake was pointed out to me. There was a few interesting, so no questions about any of this? Okay. There was a few interesting things that I wanted to address, though. No judgment. Well, I'm sorry, a little bit of judgment, but you need to take a little bit of judgment. Hands up if you never looked at this. You just didn't do it. Just be honest with me. Cool. I appreciate your honesty. A few of you. Okay. I do want you to take a look at it because there are some interesting effects that show up here. But you've got a weekend, so on your own time, definitely do go through this. Friction. There was some interesting stuff that happened with friction. Did anyone notice? I know Tanjo, you did because we talked about it yesterday. Manuel.
It's harder to move an object that's already in rest than it is to move an object that's already moving.
So, yes. How did that show up in this applet?
If you make the friction option high and you had a heavy object, you couldn't move it.
What do you mean?
Like, I could do with the fridge, the bucket, the person, so you do that with 80 kilograms, and the friction was all the way up.
Well, let's take a look at it. That is true, but that's not the weird thing that showed up. Let's load it up here. Let's stop. Let's pause the recording just because this is making it slow. So yesterday we did Newton's first law. Today we're going to talk about Newton's second. The second law, obviously, maybe it's not obvious. It should be obvious. The second law builds on the first law. And you kind of saw it in the app. Well, that was the whole point of the app that I gave you there. Newton's second law is this. A net force produces what? Sorry? In a roundabout way eventually, but sooner than that. Yeah, also true, but not yet. In movement in the form of what? What kind of movement? And but what kind of movement? Describe to me the box was moving, but what about the movement? It wasn't just moving. Sorry, I heard it. Tristan. It was accelerating. So Newton's second law is that a net force produces an acceleration. And the formula for this is the one that Manuel gave us on the first day of this unit. F net, that's a little subscript net. F net means that there is a net force. That means the sum of all the forces is not 0, is equal to ma. Or conversely, sometimes it's written like this. The acceleration is equal to, the acceleration that's produced is equal to the net force on the object divided by the object's mass. Both of these are formulations that show up. This is typically the one that you'll see, and if I'm not mistaken, that's the one that shows up on your formula sheet. In fact, there it is right there. F net equals ma. The first one in the dynamic section on your formula sheet. This also, I've said this, I wrote this down once already because Manuel brought it up, but forces are measured in what kind of units? Newtons. And these two are measured in what units? Masses are measured in? And acceleration is measured in? Meters per second squared. And what that means is a Newton, a single Newton, is equal to a kilogram meter per second squared. It has to be, because this relationship is true. Even though talking about these things doesn't make sense. If you pushed on someone else, you wouldn't necessarily talk about how you pushed on them with a force of such and such kilogram meters per second squared. You could, but it wouldn't make as much sense as just talking about it in the form of a Newton. So they're equal, and you need to recognize that. So some examples. We'll do how many we're going to do here? We'll do a few, and then I will free you to work on it. I got a bunch of practice here. A 5 kilogram block is pushed to the right along a frictionless track with a force of 10 newtons. What is its acceleration? For the dynamics section, well, even in the kinematics section, I always encourage you to write down, to draw what was going on here. In the dynamics section, it's not an encouragement, it's a requirement. You must draw what's going on here. And on the next page, we're going to talk about something called a free body diagram in a little bit more detail. But until we get to that point, let's just draw our box and our ground. It's not supposed to be hovering. And let's write down all of the forces, or let's label rather all of the forces that are acting on the box.
You got a supportive force, which is ground.
A supportive force from the ground acting which way?
Up.
Now, forces are always drawn from what point of an object? The center of?
Gravity.
Yes, which we don't call the center. We don't always call it the center of gravity. We call it the center of mass. So from the center of mass, we've got a supportive force, which we call the normal force. So we're going to label it as Fn. What other forces are acting on that object? Gravity. Gravity's acting which way? Downwards. So that's going to be our Fg. And what else? Frictionless track? No friction. There's an applied force. Applied force is what we call forces that we don't necessarily know what they are. It doesn't matter what they are, but it's a force that's acting on this object, causing it to do something that isn't otherwise determined. We just know that it's being pushed. Pushed by what? Doesn't matter. So we're going to label this thing as an applied force. I mean, you could draw it from the left, pushing it to the right. Typically, how we draw these things, though, is from the center of mass in the direction that the force is acting. So it makes it look like a pull, even though the question said it's being pushed. We draw it from the center of mass outwards here, and we're going to call this thing F applied. Is often how you'll see that written. So I'm going to zoom this in, actually make it a little easier for you guys to see. So this is the beginnings of what we eventually I'm going to formally call a free body diagram, where I've got my object and I've got all the forces that are acting on it. Let's start to fill this thing in. Can I label any of these forces? The F applied. F applied is? Sorry? 10.0 newtons. Cool. What else can I label? The mass is 5. So I can use my mass to give me the force of gravity, because Fg is equal to what? G is equal to 9.8. What is Fg equal to? Give me what's the formula for Fg? Mass times gravity. Fg is equal to mg. So that's going to be mg. So that's going to be the mass, which we know is 5, times 9.8. That's going to be 49 newtons. That is going to become a number that you're very familiar with. Lots of the objects you're going to deal with are going to weigh about 5 kilograms, or multiples of 5. What other force can I now label? The normal force has to be the same. Why? How do you know it's balanced? Yeah, there's no other force acting on it, and the block's not flying up into the sky. So the normal force has to equal my force of gravity on level ground like this. So now we can actually figure out what the acceleration here is. So to figure out what the acceleration of our object is, we're always going to start with this idea here. F net equals ma is where all of these things start. Net force, let's go back over here for a second. F net is the sum of the forces. And to make our life a little bit easier, the net force we can typically, the way I typically explain it is it's the sum of the forces in the direction of motion. So if the object's moving, all we care about are the forces that are causing that motion. So for this thing, the only force that's causing an acceleration is going to be which one? The applied force. We're told it's being pushed to the right. Fn isn't causing motion. Gravity's not causing motion because these two are balancing each other out. So my applied force is the only one that's causing motion. So that's the only one that's going to show up here in my F net equation. So we're going to have our F applied is now going to equal ma. And we can start shoving in values here. Our F applied is 10. Our mass is 5. And I want to know what the acceleration is. So what is it? It's going to be 2. 2 what? Oh, this is the acceleration. Just meters per second squared. So a 10 Newton force on a 5 kilogram object on a frictionless surface is going to provide a 2 meter per second squared acceleration. That's it. Cool? Comments, questions, concerns? Relatively straightforward. Okay, let's do another one. A 650 kilogram car accelerates at 4 meters per second squared south. What is the net force acting on it? So let's draw the thing. We have a car. This is a top view of the car. The thing has a mass of 650 kilos, so typically I just toss the mass right there in the middle of that thing. We know it's accelerating 4 meters per second squared south. So what forces are acting on my car? I do this one a little differently. It's a top view now. It's going to make it a little bit harder, but for reasons that are going to make sense here in a sec. Yeah? Gravity. Gravity's acting which way?
Down from the center of mass of the car.
How would I draw that on here? This is a top view of the car.
Yes, it would be just a point.
Put it in the center of the rectangle.
So gravity's acting down into the page. Right? Because I'm looking down from the top of my car. It's a bird's eye view. So gravity's acting straight down. The way we identify that in physics is we put a little x. Means it's going straight down. There's my FG. This is not a great way to draw it, but that's the way I'm going to draw it. So then my normal force is acting which way? The opposite direction. Well, it's not always opposite. It's perpendicular to the surface. So which way is the normal force acting? Straight up in this case because the surface is flat. We represent that by a dot. There's my Fn. What other force must be on here? Rolling objects don't experience friction the way we expect them to. Because the car, it's accelerating 4 meters per second squared.
There's
Let's ignore air resistance for the time being. Make our life a little bit easier. If the thing's accelerating south, something has to be causing that acceleration, right? Yeah, so we're going to call it an F applied. There is some applied force in the same direction as the acceleration. Because for the sake of this problem, we're going to ignore air resistance. So then how strong does that force have to be?
We multiply the weight, the mass, times the acceleration, and we got it as applied.
Okay. So I'm going to have my applied force is equal to our mass times our acceleration. The applied force is what we're looking for. The mass of the car is 650 newtons, and what's the acceleration? 4 meters per second squared. So, how big does that force have to be to cause that car to accelerate at 4 meters per second squared?
What?
You said, "Hey Siri," so she responded to you.
I didn't think she would.
2,600 what? And forces are vectors, so which way? South. Cool. Comments, questions, concerns? Relatively straightforward. Okay, one more. A 1,500 kilogram ice cream truck accelerates from rest to a top speed of 45 kilometers per hour in 8 seconds. What was the net force acting on the truck?
What's a normal truck weight?
That's pretty light for an ice cream truck.
What's like an average truck?
Like a what kind of, like a pickup truck?
Yeah.
Let's Google it. Hey Siri.
How much is it? Average?
It worked. It went on my thing.
Dude, I was asking a question.
Oh, you hit the button?
No.
Yeah, so.
She just had Hey Siri.
No, it's not supposed. It's supposed to be my voice. That's crazy.
A pickup truck weighs in kilograms. Yeah, that's a really light truck. Yeah, like a small pickup truck weighs about 2,700 kilograms. So this ice cream truck is like
No ice cream.
my Civic. I'm driving around my Civic selling ice cream. So my ice cream car accelerates from rest to a top speed of 45 kilometers per hour in 8 seconds. That thing's, yeah. What was the net force acting on my ice cream car? Well, let's draw the thing. Here's my ice cream car. Then we know the thing has a mass of 1,500 kilograms. We've got gravity acting down. We've got a normal force acting straight up. There is some net force acting to the right. That's what we want to find. Okay, well, we know F net equals ma. I know my mass is 1,500. Do I know my acceleration? Given the information in the question, could I find an acceleration?
Yeah.
How? Oh, so you're okay. So I've got a. You want me to change? So I've got a v here. You want my 45 kilometers per hour, and you want me to turn that into meters per second. How do I turn 45 kilometers per hour into meters per second? Sorry.
3.6.
Do what with 3.6?
Times 3.6
It's divided by 3.6. Yes. So 45 divided by 3.6. It's 12.5. What V is this? Top speed. So that's my final velocity. Okay. So what else do I know? My VI is going to be 0. What else do I know? The time is 8 seconds. And I want to figure out my acceleration. What formula am I going to use to do that based on the information that I have available? VF equals VI plus AT. Very good. So 45 equals 0 plus A times 8. So what's A? No, I lied. I don't want 45. I want 12.5. Cool. Thank you, Manuel. Sorry, the value was? 1.5625 meters per. I'm running out of space. So then that's the value we're going to put up in there. 1.5625. Which means my net force is going to be equal to what? What is 1,500 times 1.5625? Oh, hey. How are you? Hello. What's the value? One more time, Zaid. 2343. Point. Newtons. Cool. Done. Comments, questions, concerns? The kinematic stuff hasn't left. It's just we're going to add to it now. Okay. If I've got an object where multiple things are working on it, we've already I defined my F net to be the sum of the forces in the direction of motion. So I've got here in this example, Stan and Kyle pushing a 75 kilogram sled along a frictionless rink. The implication here is that they're pushing together. So when these two forces are working together, if I'm summing up the forces in the direction of motion, what am I going to do with these two values? I'm going to add them. So when I've got two forces working together, they're always going to add. So let's draw it out. I've got my sled, which is just a block, apparently. And let's draw all the forces acting on this. I've got gravity acting down. I've got normal force acting up. I've got Stan. And I've got Kyle. We know F Kyle is going to be 45 newtons, and Stan is 55 newtons. So when I set up my F net equals MA equation, the only forces that are acting in the direction of motion are going to be the ones from Stan and Kyle. And because they're in the same direction, they're going to be additive. It's going to be the force from Stan plus the force from Kyle is going to equal my mass times my acceleration. F Stan is 55, plus Kyle was 45. The mass is 75. What's the acceleration? What do you get? .3 repeating. Can someone verify that Zaid is correct? Okay, cool. And then conversely, now if we start dealing with things like friction, the job of friction is to do what? That's one of the things it does. Friction opposes motion. So I've got my Batmobile here, exerting a force of 8.5 times 10 to the 3 newtons east. It's the engine, while friction pulls it back. So this is friction due to what? It's not the road. Could be the air. Could be the bearings in the wheels. Could be the friction in the engine. Wherever the source of friction is coming from, we know that we're told all of the friction adding up is 1,500 newtons. So let's draw it. Got my Batmobile. Old school Batmobile. We know that there's a force I'll just call it an F applied, which I'm going to shorten to FA. We know that that is 8.50 times 10 to the 3 newtons. It's got gravity acting down. It's got a normal force acting up. And friction is acting opposite the way this thing's going. And we know that the force of friction is 1,500 newtons. And force of friction is written as F with a little subscript F. So then we need to figure out the mass of, we need to figure out the acceleration of our object. We're given the mass. So F net equals ma. How are we going to deal with the fact that these two objects are acting in, how are we going to deal with the fact that these two forces are acting on this object in opposite directions? Manuel. How do you determine which one you're going to subtract from which one? While that might make sense most of the time, it's actually not how you want to approach this. Really.
I was just thinking greater one step by the way, and just keeping in mind which direction you're going and anything that's negative.
Well, that's not a terrible idea. Physicists are lazy and don't want to carry as much. I want to encourage you guys not to carry around things in your head you don't have to. So rather than just making a mental note and hoping we don't forget it later on, the easy thing to do at this stage is to, when we're dealing with vectors, we said that there are some directions that are positive. Typically, up, right, north, east are positive. Up and left, west, south, down are typically considered negative. For the sake of these kinds of problems, though, you can free yourself up a little bit. It's up to you, ultimately, which way is positive and which way is negative. So when you've got forces that are acting in different directions here, now it becomes important for you to decide and label on your diagram which direction you want to be positive. So for a problem like this one, which direction do you want to be considered positive? Why, Manuel? Because the shape of the car is going that way. Cool. That's one reason it could be that way. Why else could it be that you wanted right to be positive? Sure. Why else? Ultimately, what I'm trying to get at here is the reason doesn't matter. Why Manuel chose right to be positive. There's a bunch of different reasons. Maybe you just like that right is positive because right should always be positive and left should always be negative. I don't care. As long as you're consistent, Because we've got forces acting in opposite directions here, we've got to start talking about including explicitly which direction is positive. It could be, Manuel, like you said before, that I want to subtract the smaller number from the bigger number. And so whichever direction the bigger force is acting, that's the direction I'm going to call positive. That could deal with how you wanted to subtract things earlier. Which means if friction was bigger, you could have called to the left positive, and then it would have been friction minus your applied force. So let's write it out. If I'm calling to the right positive, when I sum up my forces, I'm going to have Fa minus my force of friction. Right's positive and the friction's acting to the left. So I subtract my friction from my applied force is equal to Ma. So my F applied is 8.5 times 10 cubed minus 1500 equals 1250 A. What is the acceleration of the Batmobile? Sorry? 5.6 meters per second squared. And that value is positive. So what's the direction of the acceleration? Well, and we know to the right is actually which way? It's east. Cool? Comments, questions, concerns? Welcome to Newton's second law. For the sake of time, we'll do the free body stuff on Monday. We've only got like 10 minutes left in class. Skip this page. Skip this page. We'll come back to those free body diagrams later. I want you to flip ahead to here, Newton's second law, worksheet number 2. Do I want you to do those ones? No, I want you to flip one more. Flip one more to worksheet 4.1, Newton's second law. This is the one I want you to do for homework. All of it. There's only 7 questions there. And the reason I want you to do these ones is because these ones actually have the answers associated with it, so you know whether or not you're doing it correctly. On Monday, we're going to come back. We're going to look at the free body diagram questions, and then I'll give you the other 2 pages that we skipped for homework on Monday. Yes, Eric? For these questions, yes, I want you to draw. Now you got to draw. It's not a recommendation. Now it's a requirement. With the time that's left, I want you to practice this. 12 minutes, according to my computer clock. There's a bunch. You can get a couple done here in 12 minutes. Give it a shot. On your mark, say giver. You may.